and produced by the Sound of Knowledge Incorporated.
Okay. Well, narrows it down a bit. Okay. Let's wake up my machine. What I want to tell you about today is the dangers of violation of your kernel's integrity. I want to do that with the following points. First, I want to talk a little bit about what's the issue that's behind it. So, why is it a problem? How does it come about? Then I want to talk a little bit about detection. This is not really... I'm going to switch. Okay. Does this work better? Okay, about the detection, because I want to use it in a black hat way. I want to abuse the violation of the integrity in a black hat way, and what I want to do is avoid detection. So how can we avoid detection? That's what it is about. Then I want to introduce some software I wrote, which does precisely that by modifying the kernel. At the end, I will go, it depends a little bit on what your interest is. I can go deep into the functioning of the module, or I can go deep into what you could do about it. So it depends a bit on what your interest is, where I go the deepest. But first, the issue. Big issue is that root is almighty. And I'm talking root here because we're talking Unix. But you can easily swap administrator for Windows. Much of the same issues apply. So there are lots of opportunities to hack root. That's the second problem. Finally, root can change the kernel. So your kernel integrity depends on the fact if root is being used. And if it's easy, then you can easily change your kernel. And finally, if you use your kernel to detect if there is any abuse, then changing your kernel is a problem. And altogether, these problems taken together means that a kernel attack can be very effective to avoid detection. Now, the fact that you can hack a kernel and that you can change it and that you can avoid detection that way is not something new. It's been known for years, and I'm talking like 5 years, maybe 10 years in theory, but even in practical sense, it has been known for years and years. There have been articles in Frag like 3-4 years ago, so it is not a new problem. That raises the question, okay, why am I talking about it here? And I've been thinking about, is it valid to talk about it here? I came to the conclusion that it is. Why? Because there are still issues today that show that this problem is not taken that seriously. And I want to pass along some arguments that are being used. The first one is that, okay, if your box is rooted, you've lost anyway. So there's no point in trying to protect your kernel because, okay, you lost. My big question is, okay, but why is it so easy? Why every release of Solaris, because that's a demonstration I'm giving, every release of Solaris there are more statute root programs, there are more daemons with obscure functions that make it possible for you to hack root. The second argument, it's so sophisticated that, okay, this risk is not so high. It's beyond the normal script kiddie. Unfortunately, it's a scriptable thing. Once it's programmed, it's a scriptable thing. My operating system is closed source, so this is not a problem for me. Only Linux and the OpenBSD, the FreeBSD, they have the problem because anyone can look at the kernel source and modify it and in that way easily modify the behavior. But that's also not true. Why? Every operating system vendor needs people to use their kernel. Why? To write device drivers, for instance. So there's a whole lot of information to make it very easy to interact with the kernel. And there's a whole lot of publication about how the kernel works. So it isn't that difficult. And I hope to show that today. And then there's the argument that all the solutions that are there, mostly practical solutions, or I mean theoretical solutions like all kinds of trusted OS kind of solutions are very difficult to work with, or maybe impractical to work with. So that leaves the questions, okay, why aren't there any better solutions? Why isn't there much work in that area? But first over to detection. So what is detection and how do we detect an intrusion? Well, that's general knowledge. I mean, intrusion detection is now more or less a set subject, and most people know the issues involved. I've taken here some naming from the IDS FAQ. Generally, you can distinguish between host-based and network-based. So you look at what the host is doing, you look at the files, at the processes, at all the trails on the host, or you look at the network traffic. You look at the connection being made, the probes being made, and decide based on what you see if it's legitimate or not, or if there's an attack going on or not. From both these intrusion detection types, you can distinguish several ways they work. There's misuse detection, so that's using something in a way you weren't allowed to. Anomaly detection, that's detecting behavior that's outside the normal, expected behavior. And there's general system health monitoring, like is it operating like it should? Do all the function work? Things like that. If you look at all these forms of detections, they all use information that comes from the kernel. So what do they use? You have audit trails. They are written from the kernel to the file system. You have system monitoring like the process behavior. You have integrity checking, checking if a baseline still exists, if the current system compares to the baseline that was some time in the past named secure. And you have network protocol sniffing, and you try to reconstruct the state that the systems had. So what are reasons to hide? Well, you have the black hat. The black hat wants to hide his tools, his backdoors, his whatever, his sniffer logs. The white hat can also have a reason to protect or hide stuff. Maybe I want to hide my host intrusion detection software. Or maybe I want to protect my kernel through some form of hiding. Okay, we have all kinds of tools to interact with the kernel to figure out what is going on and to do our detection, base our detection on it. So first, the most well-known tool is tripwire. It's an integrity checking tool that tells us what the state of the system is. You have process accounting, how many resources are people using. You have auditing trail software that analyzes the audit trails. And then you have the general tools on your system like netstat or PS that show you information about the system. And what do we want to hide? If you think about a system and you think, okay, I want to be on this system, but I don't want to be seen by anyone at all. So what do I not want to be seen of my activities? Of course, my process. If I'm running a backdoor process, I don't want to see the process. I don't want the administrator to see the process. I want to install backdoors so that when they are run, their behavior is different from the original. I don't want people to see that. And you can go on. There's system logging. There are all kinds of derivative behaviors that are not directly, but file timestamp modifications on files that you touched. To take a specific example, because it's, I don't know, it speaks to the imagination a little bit, because this is the tool to use to see if your system is still healthy. And that's tripwire. And as I said, tripwire is an integrity checking tool. It does this by the following process. It looks at a file, the properties, the content, takes all these features as one big set of data and creates or calculates a hash over this. And it stores this hash, again, cryptographically protected. So if we want to create a system where tripwire is still calculating the correct hashes, but the system behavior is modified, we can do that by, for example, modifying a kernel call called execve. This call is used to execute programs. What tripwire is doing when it's trying to calculate a hash is not using the execve call, but it uses the open call to get the contents of the file. If I redirect the execve for a specific file to another place, but I don't redirect the open, then tripwire will always get the original, but when you execute something, it will get a modified one. Before we go into how do we modify a kernel, we have to realize what a kernel is. Now, what's it doing? Basically, the kernel is running your system. And it offers its services to the userland, to the processes that you can run on the system. What does it mean? You can ask it to create a new process, or you can ask it to give you access to a certain device, for instance, the hard disk raw drive device. It takes care for you of the separation of privileges. It makes sure that if you're in a certain privileged process that you can't access another privileged process on another privilege level. Generally, the kernel is extensible. You can add new protocols, you can add new file systems. Often, or mostly in the case of Unix, it doesn't have internal privileges. So internally, it's only on one privilege level, which is the highest, and it can do all. And what you can do in userland is ask at the kernel what the status of the system. You can ask about processes, or you can ask about the network state. You can see what connections there are, or you can see where processes are listening. And you can do this through three major means. One is through system calls, one is through devices, and the third is through the proc file system. This is a special means of interacting with most of the kernel state. So how can we modify the behavior of the kernel based on what it offers us? One of the interfaces is directly to the memory. You can write directly into kernel memory if you're root. So you can modify any structures, any code space, maybe even of a kernel by directly writing into that space. Or you can create a new kernel. You can just build a new kernel and replace it and reboot the system, and it will run your new kernel and it will do the new things. But one of the most well-known ways to do it is the loadable kernel module. Loadable modules are a design that has been added to Unix to make it more extensible. So it's, in effect, it's a good design principle to make things modular. It helps. You don't waste resources if they're not needed. It makes the design clear. It's general a good principle. The way it works is you compile your code. You ask the kernel to allocate memory for it. It will resolve all the symbols in the kernel against your module and vice versa. And when that's done, the init function is called off your code, and you can start initializing and bring it into the kernel. So to show what the effect is of such a module, I wrote a kernel module for Solaris that basically does all the hiding that you want. Is capable of fooling tripwire, and it's meant to demonstrate the serious effects that such a module can have. I used Solaris because it's a free, or no, it's not free, it's almost free, but fairly widely used commercial operating system. It's closed source. It will be open source fairly soon, but still closed source. I meant it to be easy to use because so as I said before, there are lots of places on the internet that you can find documentation about kernel modules, but there are not so many modules that are really ready to use. You have to do a lot of work to get them into a fashion that you can use it reliably. I tried to demonstrate several ways to change the kernel. So the most well-known way is to change system calls. I tried to use some other ways. And I made it open source so you can look at it, play with it, and see the effect. So how do we start? The first thing is that you have to think about, okay, what do you want to fool? Where do you want to hide? We talked about it a bit earlier. And then you have to look at a kernel and see how it functions and how it keeps track of what its state is and what it's doing. And there are three main items that it's using for this. The first one is the switch table. A switch table is basically a big array of pointers to functions. So you give them all the functions, you give a number, and you say, okay, I want to call a certain function, and I call number 3, and you index in the array and call the specific, for instance, system call. But there are other switch tables in the kernel. Another one is linked lists, which is really good for extensibility because you just link in more objects for whatever type of object you have. And global variables are also very useful. So this is what I just described. You can change function pointers in the switch table. You just override an entry in the array with a new function that you wrote, and you take care of saving the old function pointer, and you can reuse it in your own code. Hiding in linked lists is also fairly easy. It's only not so easy if the kernel wants to walk that list regularly for tasks that are essential. If they are tasks that you don't want, then it's good. For instance, the loadable kernel modules themselves are, their state is kept in a linked list. So if I want to hide the module that I'm loading, all I have to do is make sure that the linked list no longer refers to my module. I just readjust the pointers of the linked list to cross over my own module, and it is no longer visible in the system. So some other stuff you want to hide. you want to hide processes. So how do you find processes in your system? As I said, you have the proc file system, which is very much geared to interaction with processes. And you have the direct kernel memory. Both are used by different programs in your system. For instance, LSOF, which is a program to inspect a lot of kernel state, is using kmem on Solaris, but most of the Solaris tools themselves use proc. You want to hide the backdoors, the thing I talked about earlier. And you want to hide files. You want to store stuff on the system. You want to have your host-based intrusion detection system maybe, and you want to hide those files. This is a little bit of a code demo of how the exec function is done. I don't know if it's really clear because more or less cut and paste, so it might be a bit hard to read. But what you see here is the way the prototype is defined on the Solaris system. So you can just read the kernel headers and you see, okay, there's an exec function and these are its parameters. So you write a function with the same interface. What I want to do is I want to have a new execve. I save the pointer to the original in that switch table. I write my own. I put my function pointer, my new function pointer in the switch table. And in my own code, I just call the original. So I don't have to code the whole execve function from scratch. I just do some pre-processing, call the original, and maybe do some post-processing. And that's a really nice way to do it, because if there's a system upgrade and the behavior is modified, there's a patch, a kernel patch, then it still keeps working because the patch is in the original code and the module doesn't need to know it. So what do we want to do in this execve function? In the new one we put in our module. We want to test if the binary we are calling is the one we want to backdoor for. So if is this the one that we want to redirect? If it's not, then okay, we just pass on to the original. If it is, we want to change the argument that's passed to the execve call to the new program, the one that we backdoored. Also, there need to be some checks and some changes in your module to make sure that you can, for instance, call a backdoor that's in the hidden section of your file system. Now, this is a whole lot of code. It's not very clear. Maybe in the handout, I'm not sure. But basically what it says is, okay, if we're in the kernel, look up the argument, test it against our own internal linked list. So the backdoors, there can be multiple backdoors, and they are put on a linked list. And you just compare till you find a match. And if you find a match, you replace the argument and call the original. So it's really fairly straightforward. And what happens is this. If on my linked list there's an entry that says the backdoor is, this is a bug in my sheet. The top line that says my login is wrong. It should say bin login, because we're not looking for my login. We're not looking for someone trying to execute my backdoor, but we are looking for someone to execute the original. If it finds the original, or if it matches, it will replace and will execute actually bin my login. But the open will still open bin login. So tripwire will still do the right work. Now, I will fairly quickly go over some calls that I changed. As I said, system calls is the most popular way to do it. If you look at all the things you can find on the net about kernel modifications, they all use system call modifications. I only used these 6. They are only to do with the exec redirection and with process hiding. So a feature that I built in is that if a process is hidden and it forks off a new child, the child will automatically also be hidden. So that's fairly easy. If you have a backdoor that's hidden and you come in and the shell is spawned, then the shell also will be hidden automatically. The kill and the seq are signals that are sent to the backdoor, to the process, and it's to catch a trick that was suggested by Thomas Pacek, is to send a signal to all PIDs that you can imagine. So you go from 0 to 65,000, and if the process responds differently than what you'd expect because there's no PID in the proc file system, for instance, then you have found a hidden process. By catching kill and seq, you can just say, okay, there's no process, and you won't find it. What I did replace a lot is the file system calls. There are switch tables for different file systems, so you can extend it and you can add new file systems. For instance, you have the proc file system, you have UFS, which is the default normal file system. You can have all kinds of journaling file systems, NFS file system. I had to do quite a lot of these because of two issues. One is the general file system hiding, but there's also a feature to survive a reboot, and that needed a few more. And then there are a few others. Def kmem, to hide from LSOF, you need to catch the mm read. And for netstat, it will also hide connection on a certain port. Here it says still 2 functions, but I changed the code and it's now only 1. It's only the last. So what is doing with all these functions? As I said, first process hiding from proc and from def kmem. For all the processes that have a hidden flag. If you look at the kernel headers, you get a description of what a process structures internally look like. And most structures have a flag field. And if you look at the definitions of the flags, then you often find that not all flags are in use. So you can use these flags that are not in use, or at least you hope they are not in use, because you don't know for sure. They're just not in the kernel header, but it's a good signal that it won't be. You can use these flags for your own purposes. So you can put a flag that it's a hidden process, and it makes it easy to check on other places if this is a hidden process or not. Okay, fork, as I said, will hide children. Signals to hidden processes will fail. If you use netstat, it collects information about the state of the network interfaces. It does this by sending a message on what's called streams. Streams is a way that's, I think, sysv Unix, where you send messages on a queue, and everyone on the queue can look at a message, see if it's for him or her, and maybe reply to it. So what the module does is it goes sit on the end of the queue and watches all the messages go through, and if it sees a reply to a netstat inquiry, it will parse the code and remove some entries with a certain port. File and directory hiding is done by prefix. It's also done with a flag to create a system where not every directory listing and every file access needs to be checked, but only those where the directory also has a flag. So that what you can do in that way is make sure that the timing differences between a system with the module and a system without a module is not that different. If you have big directories where you have to go through all the files in the system to see if your prefix is there, it can show up as a clear time difference. Okay, stat is changed to the main reason is for a property that's on a directory that says how many directories and files are in there, and that's used by tripwire. So you want to change that. And finally, it's made reboot proof, and that's one distinction between a system where you use loadable kernel modules and it's not reboot proof, is that you don't need to touch any system file at all. You don't need to change any files at all to do what you want to do, what I described. if you want to make it reboot proof, you at least need to change one file somewhere in the system, because when it's booting up, either you want to have the kernel itself changed, or you want to have some system file changed, so the kernel will at some point load your rogue module. So how did I implement this reboot proof feature? I decided to replace one of the system modules. Solaris is a completely modular kernel. Almost all the stuff that the kernel does is in a module, so it needs to load like at least 100 modules for it to function normally. So it's easy to find some module that you can replace with your own. So what you do is you move the original module to the hidden prefix name. So that one will be hidden if the module is loaded. Then you put your module in its place. Then you have to do a whole lot of magic to make, for instance, tripwire still believe that your module is the original, which is a lot more work than it is when you just want to hide. And then when the kernel boots, it will load your module instead of the original, and your module can do a load of the original. So that way it will survive a reboot. So now I prepared a little demonstration. What I will do is, I have two systems. What you see here is the Solaris system. I hope it's a bit readable. It's a bit strange characters. And on this system, I will shortly show the attacking system, which is the laptop on top. What I use is a standard remote exploit for Solaris 7. It's a CMSD exploit. And I will use that to copy in the kit, the kernel module kit to the Solaris system, install it, and show you from both systems what you can see. And you will see that on the Solaris system there's not much you see, and on the attacking system you can see your module. Then we'll do the reboot check also. Okay, so this is the attacking system. To show you the exploit, it's quite simple. It's just the CMSDX with some arguments. And what it will do is it will rcopy the attacking code from the attacking system to the temp directory and start a backdoor. So all you have to do is start this and hope it works. Okay, so this was a simple exploit, right? This is just standard stuff. I'm now logged in on the backdoor port, so the exploit and the backdoor I just took from internet yesterday. So the next step is, okay, I'll switch to the temp directory. You'll also see all the time the not found, but that's because it's a lame backdoor. Normally you just have a shell. So next step, I will copy the kit from the attacking computer. Okay, what you see here is, okay, the kit. I just took it over. It's just a binary kit compiled. You see, let me see if I can point. There are a few scripts. Basically, the only one that's interesting is the install perm. There's a permanent and a single shot module. Basically, what this will do is the whole process that I described of replacing the original kernel module from Solaris It will install also the single shot one for the current time, because you don't necessarily want to reboot. It will also install a backdoor of login. All this will do is show a banner above the login prompt so that you can see that it's not running the original. Before I do this, I first want to show on this system, it's still a bit harder, that we have tripwire on this system installed. Now, the whole screen will scroll, but somewhere there will be a line saying no violations. So, and I just set it for the specific directories and stuff that I'm using. And we'll show in the end that if you unhide it, that it will find it. Okay, so install perm is just one enter. What I want to do now first is still hide the backdoor that I'm running now, so I have to find it. Whoops. This is not handy with my... So the process of the backdoors is PID 315. I can also see that here. Whoops. Okay, so now I give this command. Oh, damn. Okay, it's gone. So what I did here was with the mod control, I said hide this PID, and for the Solaris system now it's hidden. So the only window that you have is during the attack. If you have normal host-based intrusion detection that would detect the standard exploits, then okay, this would have been a time that it could already detect the attack. But from this moment on, it will be unable to. This module installs itself in etc scal. Whoops. I forgot to hide myself. So what we see now is the difference is here there are 3 programs. Now suddenly here there's an hide me. This is the directory with the hidden stuff. Well, as you expect here. Wait a minute, I'll start another shell. Yeah. Okay, it's still not there. Okay, tripwire still doesn't see anything. What happens if I oops. Okay, the login is backdoored, but tripwire still doesn't see it. Another thing is network connections. There's only evidence of the telnet I just did, but not of this one. The connection on port 8080. So are there any things that you might see to see if it's detectable or not? Anyone got an idea of what might be possible to still see on the Solaris that there is something installed? Sorry? Okay. The question is to compare the DU and DF for the directory with the hidden files. The DF will be a bit hard because it's not that much, so I don't know if it will show up much. Okay, it says 10 here. I have to say I have no idea because I've never done it before. Whoops. So clearly it doesn't see it. Now there are some tricks because there are lots of ways. For instance, simple thing is already raw devices. The module doesn't hide anything on raw devices. But there's another way you can look at a file, or more specifically at a directory, and that's with cat. You can just do and there it still is. So the difficult part of really hiding anything, or everything I should say, is that there are lots of ways to look at a system. And this is one, because what you do here is open on a directory instead of list the directory contents, and that one is not intercepted, so you still see it. But generally, if you can think of something that is detectable, you can think of a way to circumvent it. In that sense, it's just a chicken and egg problem. Okay, yeah, there's else of course. So I can say else of the PID, I think it was 315. Ah, that's a good one. Because it's still working. This is a bug in software. I have two different kinds of modules, one for initial loading and one for rebooting. And the one for rebooting, if all is well, will hide it. So there's a little slip up. I now will reboot, better do it from here. Reboot the system, and then I'll go over some other aspects and look some more at what you can do about it. And then we'll come back and see if the backdoor is still there. First, maybe some other issues that you can do that are a little bit more advanced. The first one is, especially on the Unix systems, it's fairly easy to say, okay, we just disable loadable kernel modules. Linux, it's not so much anymore. On the BSD, it was still not so much in use. So you could say, okay, we just disable the loadable kernel module feature, and then no one can load a kernel module. But as I said, you can still copy directly into kernel memory if you don't prevent that. And it has been shown that this is a workable solution, that you can insert code in the kernel in this way. You can have in-kernel daemons, network daemons, so you can copy all your code into the kernel code, and so not have a real process, but just something that lives in interrupt context or something. You can try to modify the executable code of the kernel itself. Normally, executable code is not writable, so it's read-only memory. But it has been shown in Linux that you can write also in the kernel code space. What you can do is that you don't need to override the syscall table. No, you just will override the first few instructions of a system called routine. And in that place, you will intercept the code, redirect it to your own, and maybe return later to that same piece of code. But you don't need to change the kernel structure, the kernel syscall table or whatever table. So hashing those and checking those won't work either. Of course, checking and hashing the code segment will. Another interesting feature is changing the network protocol itself. Of course, if you have a system like this, it is easy to add, for instance, IP filter. Is anyone familiar with IP filter? Okay, IP filter is a kit by Darren Reed, and it is basically also a kernel module. It is a firewalling kit. It allows you to specify all kinds of filtering rules. But you can just use it in combination with this and use it to redirect traffic, only it's not visible to the normal administrator that it's going to a different port, for instance. So you could, for instance, have a backdoor which is just listening locally on a local port, on the local interface, and redirect port 80 traffic from a certain address or with a certain IP ID or whatever, and redirect that to your backdoor. So what you will see is normal HTTP traffic, and only because it's from a certain address, it will go to a backdoor port on the local host. And it will be very hard to distinguish that from legal traffic to that same port. You can snoop TTYs. It's also fairly well known. You have loadable kernel modules to tap. Okay, this is my IP filter story. So, the interesting part, of course, is also what can you do about it? As I said, I'm giving this talk because I think there are solutions possible, or at least there should be work on them, because it's a serious issue. So what are solutions? A well-known one is Securelevels. It has been in the BSDs for some time now. OpenBSD is specifically gone very far in auditing and making sure that this works right. You can reduce the use of root by a fine-grained access control mechanism. You can have user-land programs that try to figure out what's happening to your system. As I've shown with tripwire, it's really hard to do that because, okay, what should you believe? You can try to read kernel memory, but are you reading the real kernel memory or some other kernel memory? And you can go in the kernel with your checks and try to make hashes, for instance, of the structures that you're trying to protect, and periodically try and see if the structures are still consistent. The problem you have there is that it's a chicken and egg problem. I mean, who gets there first, and how is the other going to determine if nothing changed or if there's something wrong going on? One system that's doing it at the moment that has been released like a month ago, I think, is called IPD, I think Integrity Protection Driver. It's for Windows. It's from Pedestal Software, but it's freeware. And it works as a device driver and tries to do it this way. To go a little more deep into the secure level thing, what it really does is, okay, it's like, it's black and white. It says just, okay, I think there are now 3 or 4 levels, but it's like you have root. Root can change anything, or you have root and it can't do anything. And that's your more secure level. So root can't write to kernel memory anymore, can't write to raw device drivers anymore, can't load kernel modules anymore. And basically, you just shut root off a whole lot of features. It's a system that I think it works well. But to work with it is not so easy. But then again, that goes for a lot of the solutions. Another one is fine-grained control. So you say, okay, we have a root and we know it, but we don't want to use it for so much anymore. So all the programs that now need root for stupid little tasks that you don't think are so much important, you can have special privileges for each and every one of those tasks that you need, and just give any program the specific privilege to do that single task. And so you can do other things. If you can bind a low port, you can't write to kernel memory. Examples of these are systems with capabilities, so that's Linux, the road that Linux has chosen to go. Another addition to such systems is mandatory access control, where you say, okay, we're going to label all kinds of data and objects in my system, and we're going to make sure that within all kinds of levels, they can't talk to each other, and you can't transition from one to the other if it's going to a higher privilege. Examples of those are also in freeware available. Specifically, Trusted BSD is now working on implementing these, I think, according to POSIX standards. There's a Trusted Solaris version. I've never worked with it, so I can't comment on how easy it is to use. But what I find it surprising is that it's so little in use. Then there's Pitbull from Argus System. There was a talk previously in the other hall by Argus Systems. They have something like a slap-on to a normal Solaris to make it a trusted operating system. And there's recently also a new concept that I like. It's called the FreeBSD jail. It's developed by Paul Henningkamp from the FreeBSD team. What he really did was take a chain root. I'm not sure if everyone is familiar with it, but it's like basically a file system jail. It just says, okay, you can't go out of this file system area. And it's taken a step further by limiting also the process to what it can do on the network and what it can do with processes. I heard a comment that from someone working on Mac system that it's a bit like a Mac system with one label. You just say you're now running with the label Jill or you're not. And for Jill, these kind of configuration parameters apply. So what it really does is make the configuration problem that you have when you have a full-fledged trusted operating system, which has lots of levels, lots of complicated interacting issues, simpler to maintain by just using it for a specific purpose, probably, but also for a whole lot of useful purposes. So what about Windows? Well, pretty much the same problem. It's also got a high privilege level that can do almost anything. It's also used for all kinds of tasks. There's an open source project going on called rootkit.com by Greg Hoagland. So, as I said, there's also now that integrity protection daemon. So, I think there is pretty much the same trajectory as I have here for Unix. Okay, and finally, I want to thank Gene Kim for supplying the tripwire copy, because what I demonstrated here is that tripwire is foolable, but that doesn't mean that tripwire is useless. It's important, it's an important tool, and it's just that you need to do other things as well to make it worthwhile, and that you also need to acknowledge that there are other problems that you need to address aside from running tripwire on your systems. And there are some references of sites and things I used for the development of the module, and the URL of where you can get a copy of it to play with. So now I want to go back to the system for a short moment. And basically what I'm going to try and see is if I can still go back into the system now. Okay, so it still works. Let's see if tripwire has found something yet. Still nothing. I am curious now if my backdoor still is hidden from else-off. Okay, the PID is 273. I see it here. So we. Okay, so also finally submitted. So now the final check is to see if tripwire does see the additions and changes if it's a hidden process. I need to figure out what the shell is, so it's 255. Oops. Okay, we found them, so luckily tripwire does work. And that pretty much ends my presentation. Thank you. Are there any questions?